Hello everyone, and today we will start another session on modular multi-level converters. So, in today's session we will mostly talk about the different circuit possibilities with MMC. Okay. Or modular multi-level converter. So, in this lecture session, the usefulness of MMC for a wide variety of applications in power electronics can be understood by observing that this converter with the help of these controllable voltage sources can be manipulated in a wide variety of fashions, and we will see why this converter is so exciting both for researchers as well as for the industry, because it opens up a lot of possibilities in terms of different types of circuit topologies that are possible using this controllable voltage source approach. And so, AC to DC, DC to AC, AC to AC and even DC to DC, all applications of power electronics, they can be explored with the application of MMC as the main or the main principal idea, based on that principal idea. Now, usually MMC is applied for high voltage and high power applications, because we would like to have many number of low voltage switches working together, and we would also like to have the modularity feature, where there are large number of identical sub modules working together. So, these two features are very promising and interesting for MMC. So, we would like to preserve both these features, the modularity feature and the use of low voltage switch, this feature, both of these features we would like to preserve when we talk of other applications, when we talk of say DC to DC MMC, okay, or we talk about AC to AC MMC based topologies. So, modularity and low voltage features are preserved or maintained. Okay. And so, earlier or like means MMC has now been popular for high voltage DC transmission. So, where you convert the AC into high voltage DC for HVDC transmission, and then at the inverter station you convert back the HVDC into AC. So, AC to DC and then again DC to AC, that is how MMC has been commercially implemented. But people see a lot of possibilities with other types of applications, say AC to AC, direct AC to AC converter or DC to DC converters. So, these are some of the things that we will talk today. So, before I go into these different circuit possibilities with MMC, let us again recap once more what is the circuit. So, this circuit MMC circuit has many cells, and these cells are as you can this is so these are the cells here, and there are large number of cells in the upper and the lower arm, and we had said that these cells can be made up of half bridge or full bridge circuit, and these cells can be treated as a controllable voltage source. So, you can see here 3 controllable voltage source in the upper arm and 3 controllable voltage source in the lower arm, and then you have the grid or the AC side or the motor here, and you have a DC side here. So, you can send the power from the grid into the DC side for HVDC applications, like for power flowing from this AC to DC for HVDC, and power can also flow from DC to AC when you want to invert it back. So, these 6 controllable voltage source is, or these 6 controllable voltage sources are the are something which we can manipulate, okay, because these are controllable voltage source and they can be controlled easily by giving a certain reference waveform and using pulse width modulation, okay, multi-level pulse width modulation, say level shift PWM. So, these controllable voltage sources are something which we can manipulate at our own will, okay, and this is the basis of exploring the different circuit topologies. So, you have controllable voltage sources in your hand which you can manipulate and obtain the desired result. So, this is what we will explore now. Now, the first one which we will see is the same control, the same MMC, but now I have drawn it in a slightly different fashion. Why have I drawn it like this fashion? We will understand a little bit later, but you can see the same converter, I am now redrawing it in a slightly different fashion. You see here in this one we have this side, this is the AC source or load, whatever you may, this is the AC side which may be the grid or the motor load and which corresponds to this here, okay, and we have put an additional inductor. So, let us not talk about that inductor, but you have the AC side here and this AC side is here. Okay. Now, these are the 6 controllable voltage sources. Okay. So, this is the 3 controllable voltage source, this is the upper arm and this is the lower arm, and these are the arm inductors. Okay. So, this here corresponds to this upper arm here. Okay. You just see that I have drawn this circuit only, but now in a slightly different fashion. This is the circuit here. So, this is the upper arm here and this is the lower arm here. So, the upper arm, for example, is connected to one point of the incoming or outgoing AC, and here you see the lower arm is also connected to this point here. This is the common point which is same as this point here. So, this is the upper arm, this is the lower arm which is going to the AC side, and here also this is the upper arm, this is the lower arm, and they are going to the AC side. I have put an additional inductor here, just this you can ignore for the time being. So, this is here and this is upper arm and lower arm. Similarly, in the B phase also this is the upper arm and this is the lower arm. So, this is the B phase here, upper arm and lower arm, and in the C phase you have upper arm and lower arm. Okay. Now, these upper arms are shorted here, the lower arms are shorted here. So, you see here the upper arm, 3 upper arms are shorted at this point and the lower arms are shorted in this point, okay, 2 isolated neutrals, right. And these two are the terminals which say for a DC to AC converter is connected to the DC source, and for an AC to DC converter we produce the DC here. Okay. So, in a similar way, see these are the 2 neutral points, isolated neutrals of the upper arm and the lower arm, and they are taken out and shown by this A and B. So, this circuit here, the way I have drawn it is is same as the previous circuit, only it has been redrawn in a separate fashion. So, in this one, so this circuit, as we have already discussed in length, they can be used for AC to DC or DC to AC application. So, if you have if you have say a DC to AC application, then here is your DC bus. Okay. That is what we have seen in this circuit here. This is the same circuit, the DC to AC converter. You have a DC. So, if you want to create the HVDC, so you will say that okay, between the point A and B are the positive and negative terminals of the HVDC line. So, half bridge cells can be used in this controllable voltage source. Now, some researchers, so you will see in literature when you explore the MMC different circuit topologies, you can see many literatures available in online libraries. For example, if you see in IEEE Explore, then you will see a lot of circuit topology variants of MMC. Now, some researchers call this as double star chopper cell. Okay. Now, why it is double star and why it is a chopper cell? So, chopper means half bridge. So, they use the word half bridge for chopper and full bridge for bridge. Okay. So, it is a different nomenclature meaning the same thing. However, you will see both these terms used frequently in literature. So, I would like to introduce you that sometimes people call the half bridge as chopper and full bridge as bridge. Okay. So, some researchers call this topology, that is the conventional MMC for AC to DC or DC to AC application, as double star chopper cell converter. So, chopper cell you can understand because it is made up of half bridge, but why double star? The reason of double star is, you can understand here that there are 2 star connected, as if there are 2 star connected converters here. Okay. Remember that this is the upper arm and this is the lower arm, and they are fully controllable voltage source. Okay. So, if you see that the point A here, or this point here rather, I will say this point and this point, these are 2 isolated neutrals. Okay. So, this here, this one, this is as if a star connected voltage source. Okay. And this is another star connected voltage source, right. So, these 2 star connected voltage source are working together, and that is why this word double star is used. There are 2 double stars, there are 2 star connected voltage sources working together, and they are made up of chopper cells, means inside this is made up of half bridge like this. Okay. So, that is what is meant. Now, if you note it carefully, you will understand that the cascaded edge bridge converter, which we had discussed earlier, cascaded edge bridge converter is nothing but a subset of MMC. Okay. In case of cascaded edge bridge converter, we had in the cascaded edge bridge converter, we had actually only this much, only one of this. Okay. The second one was not there. This second one, the second controllable voltage source was not there. So, you can see that if I just erase this point, so this was not there in a cascaded edge bridge. So, a cascaded edge bridge can be termed as single star bridge cell, okay, because in a cascaded edge bridge we usually have full bridge here. Okay. We will have full bridge, but it is a single star. Okay. And then in that cascaded edge bridge, we had earlier seen that this neutral point here was floating. Okay. It was floating with respect to the load neutral point here. Okay. So, and we also understood that during fault condition, the voltage difference between this neutral point and that neutral point, this voltage difference makes it possible to produce balanced line voltages in spite of having unbalanced pole voltages. So, there will be then a voltage difference between this neutral point and that neutral point here. Okay. So, this one and this one. So, the cascaded edge bridge is nothing but a subset of MMC where this star is absent. So, there is a single star. So, this was only present. Okay. So, the if you analyze it in that way, you will feel that okay, we have already analyzed one single star, we have analyzed this cascaded edge bridge. Now, we are connecting one more star. Okay. So, this is also another way of looking at MMC, okay, as if like you have so yeah. So, therefore, this is where the DC voltage is available, this point between A and B. Now, this converter, so this we have studied in details, and we have seen that it can be applied for HVDC and motor drives, etc. Okay. Now, if you go one step ahead, we have so far said that okay, the voltage between points A and B are DC. Okay. We have analyzed it in details that okay, the voltage between point A and B is a fixed DC, a straight line, and then we have the AC which is being produced here. Okay. Now, the next step is, can I have a single phase AC between points A and B? That means, I will try to put a single phase AC here. Is it possible? Yes, in fact, it is possible. Okay. How do you understand the operation? So, in order to understand the operation, you see here you see that how did we analyze, yes, this slide. So, here we said that okay, there was a DC here and a DC minus DC here and the AC was inside, okay. And the upper arm and the lower arm, they were producing voltages which are given by these arrows. Okay. Now, if instead of this flat DC, if we have an AC, I mean to say that instead of this line being a flat line, can we have a fluctuating line? So, for example, not this one. So, see, we have a flat line here. If I say that okay, let me have okay, instead of this flat line, instead of a flat line, I have started to vary this line. Okay. So, what will happen then? 2-3 things will happen simultaneously. First thing, it will be possible to operate the converter, because now if the line is something like this, then the arrows can produce this blue line with the help of the arrows. Arrows are nothing but the controllable voltage source. So, the arrows will be now changing like this, okay, something like this. Sorry, yeah, we will change this. So, the arrows can produce this voltage. Okay. The arrows must be bidirectional in nature, because sometimes the arrows will be positive and sometimes the arrows will be negative. So, okay, just we will change this slide. How the AC quantity, how we can get an AC from a 3-phase AC, how can we get a single phase AC from a 3-phase AC, can be understood from this diagram here. Okay. So, here we had assumed that there was a DC source which was represented by this line here and this line here, and there was an AC which we were trying to produce, or which we were getting from this AC side. Now we are saying that this AC, this DC here is no longer a fixed line and it has started to vary. So, I can draw this variation. So, for example, I can say something like, okay, this is the AC, this is a single phase AC. Okay. So, this flat line here and this flat line is no longer a flat line. So, it is not a fixed DC, but this has started to vary, okay, slowly. Suppose you could start to vary slowly. What will happen then? You see, the arrows can still produce this blue line. Okay. So, here how will the arrows look like? So, the arrows will look like, say, so the arrow is the instantaneous difference between this blue one and the black one. So, here you see, for example, some arrows will be like this, say the green one will become like this. Okay. So, these indicate that we need a bidirectional voltage capability from the arm. Okay. So, but it is possible to have a single phase AC from a 3 phase AC. That is what we were looking here. So, here we were saying that okay, we have a single phase AC and we have a 3 phase AC. Now, earlier we had got a constant DC source and now we are getting a single phase AC source. So, that means single phase means the voltage magnitude here will vary. Okay. So, this is what also is shown here. Okay. So, the voltage is varying, right, voltage is varying at this point. So, what we understand that blue colored waveform which we had drawn, if the voltage starts to vary there, then we will be using full bridge cells inside this, we will be using full bridge cells here and here, so that the instantaneous voltage difference between this voltage source here and this voltage source here can be supported by the arm voltages here and here. So, we are basically applying the Kirchhoff's voltage law and we are seeing neglecting the inductor drop. You can find out yourself that what will be the expression of the voltages of the upper arm and the lower arm when this side is a single phase AC and this side is a 3 phase AC. Note that this single phase AC can be a different frequency compared to the 3 phase AC frequency. So, this side can be 60 hertz, this side can be 50 hertz. Okay. But here what we are seeing is a direct conversion of a single phase AC to a 3 phase AC with bidirectional power flow. Power can flow seamlessly from this side to this side or this side to this side, okay, because it is an inherent feature of the converter. So, what we are understanding is that this voltage between A and B is not necessarily will be kind of like a DC, it is not necessary to have this DC. The voltage between point A and B can be a single phase AC also, okay. And where can it be applied? It can be applied in case of say traction drives. For example, suppose in India we have 25 kV single phase 50 hertz traction drives, 25 kV single phase available on the traction lines, and suppose we want to drive a 3 phase load. Okay. So, it is possible to use such a converter directly. Okay. Now, as I told you, if we want to run under such a condition, then we will need full bridge cells, because I had just now drawn it, because you will need bidirectional arrows. Okay. We need bidirectional arrows. So, if we need bidirectional arrows, that means we will need full bridge feature. So, we cannot use half bridge. So, we have to use full bridge in this voltage source. So, therefore, some researchers call it double star bridge cell. Okay. So, because there are double stars, so there is one star and this is the second star, okay, and we are using full bridges. So, they are calling it bridge cell. So, double star bridge cell, okay, full bridge. Okay. So, the earlier one where we had used only the half bridges, there the word double star chopper cell was used. Okay. So, you can see here that we have actually done some simulation as well as experimental work on this, and you see that during this condition Okay. The so suppose this is the one phase of the three phase source or load. I mean, this does not have any means the power can flow from the single phase AC to three phase AC or three phase AC to single phase AC. So, suppose this is one side of the three phase AC, one phase of the three phase AC, and you can see here this are the these arrows are indicated, this VAU, that means and these dotted arrows are VAL, that is the upper arm voltage waveform, instantaneous upper arm voltage waveform and instantaneous lower arm voltage waveform. Okay. What are these green and red ones? This is kind of like the voltage between point A and B. Okay. We have drawn two of them just to show that how the upper arm and the lower arm instantaneous voltages can be obtained. There is basically only one of this waveform. So, there is one single phase AC and there is one three phase AC, but at a different frequency. So, if you see the arm voltage here, if you see the arm voltage, you can see the arm voltage has many steps because it is a multi-level converter having many steps, but there are two frequency components here, because we had simulated it with 50 hertz single phase I mean 50 hertz and 60 hertz both. So, one side was 50 hertz and the other side was 60 hertz. So, the arm voltage has both these frequency components, and this is expected because when we were converting from DC to AC, the arm voltage has a DC component and an AC component. Now, the arm voltage has both components, both AC components, no DC component, one 50 hertz and one 60 hertz for example. Okay. So, and the arm currents will also have a similar feature. Okay. So, this is something which is very interesting, because just by analyzing and just by looking at the circuit in a slightly different fashion, we see that a possibility exists for converting a single phase to a three phase or a three phase to single phase at different frequencies and different amplitudes. Both are possible. Now, we see the next possibility. Okay. What is the next possibility? I mean, there are many possibilities. I am just showing you some of the possibilities, and you can yourself understand why the converter looks to be a very promising solution for many power electronic application. Now, here so far you see we have considered a double star configuration. So, we had upper arm, 3 upper arms and 3 lower arms. Okay. So, there were double star, 2 stars, star 1 and star 2. Now, if I add one more star here, one more star like this. So, we will say it as a triple star bridge cell, triple star bridge cell. Now, this is something which is very interesting, because now we are seeing a possibility of, you see, a 3 phase to 3 phase converter, direct 3 phase to 3 phase converter. Direct 3 phase to 3 phase converter, one 3 phase. So, this is one 3 phase. The word incoming and outgoing does not have impact here. So, there is one 3 phase system here, there is another 3 phase system here. So, it is a direct integration of 2 3 phase systems through this converter. Now, what is done nowadays when you want to convert from one 3 phase to another 3 phase system? Say for example, you have a 3 phase 50 hertz incoming and you want to drive a 3 phase motor at say 10 hertz. So, this is a basically a 3 phase to 3 phase 3 phase to 3 phase system. Okay. So, one side 3 phase is at 50 hertz at a certain voltage, the other side is at another 3 phase at a other voltage and other frequency. So, what do? We basically first rectify the incoming 3 phase. With many times we use a diode bridge rectifier and we get rid of the frequency component, the AC component, because diode bridge rectifies it. So, we get rid of the AC component. So, we get rid of the 50 hertz and we get a DC, and by using say an inverter or on the output of that DC bus, we get a variable AC which we will feed it to the motor. So, first the idea is get rid of the AC component, make it DC. From that DC you produce whatever AC you want to produce through the help of the inverter. That is the basic idea. But again you see this is a two stage conversion. Okay. You can, instead of using a diode bridge rectifier, you can also use a front end rectifier. Okay. So that you can get some additional benefits like unity power factor operation and something like that, and bidirectional power flow. Now, this is a different way of looking at it, where you see this is one side is an AC and the other side is another AC. With this front end converter, a DC bus and the inverter, the drawback is as the voltage level goes higher and higher, this central DC link is something which making that central DC link is somewhat challenging. Okay. And because as the voltage goes up, you have to build a capacitor which is able to sustain that high voltage, and the energy stored in that capacitor also becomes very large, because it will be proportional to half CV square. So, MMC does this in a slightly different fashion, as I am showing you here. MMC is doing it, but then instead of that central DC link, it divides the DC link inside the cells, okay, as if it is doing like that. So, that central DC link is split into several small DC links inside the cells. Okay. So, this may be useful at high voltages when you directly want to convert high voltage to high voltage for two different frequencies. This may be quite useful, but it has also some drawbacks. Okay. As you have seen that there will be a circulating current, MMC is inherently there is a circulating current flowing, and the capacitors must be designed so that their voltages do not fluctuate too much in presence of this circulating current. And so, although we split the capacitor into cells, each individual capacitor, the voltage rating and the energy inside the capacitor goes down, but the total energy of all the capacitors is much more than the energy stored in the central DC link concept. Okay. Because in a central DC link concept, the ripple part goes through the capacitor, the DC or the net energy flows from the rectifier into the inverter side, but the ripple part circulates inside the capacitor. It is not the case here. Okay. This is different. So, we see that MMC gives us another possibility of using such three types, means 3 star cells for conversion from an 3 phase AC to another 3 phase AC here, bidirectional power flow at different voltage and frequencies. So, this can be connected to a motor and this can be connected to a grid and or vice versa. So, some researchers call it as a triple star bridge cell, and it is also called sometimes modular multi-level matrix converter, MMMC, that is also used, this word is also used. There is yeah, but going one step ahead, we can also see that if we connect one more of this star cell, so I can connect many more star cells like this. So, I can also extend, so one more here, I can also do like this. So, A, B, C, D and so on. So, in general I can say that an M phase to N phase system is possible. Yeah, it is possible to do like that. Okay. So, this is also something which may be interesting for certain application. Okay. So, a 3 phase to 3 phase possibility exists with MMC. So far we were talking about only star connected cells. How will it look like with a delta connected cell? So, this is what it looks like in a delta connected cell. Okay, delta connected. So, where do we use delta connected configuration? Sometimes we use it in STATCOM or energy battery energy systems. Okay. So, with the STATCOM, so this is how you can also connect the MMC the arms in a delta connected. So, this is a delta connected system here. So, I mean what we have drawn here is something like this. This is what is, so this is the same thing, I am drawing it like this. Is the same thing which I have drawn. So, this is the delta connected system. Okay, the same thing, these are same. One feature of the delta connected system is that you can have a circulating current flowing inside the delta, which may be useful when you have to compensate unbalanced loads, for example, in a STATCOM application. So, this can be kind of like a delta connected STATCOM. Okay. You can similarly have multiple delta connected systems, that is also possible, so like double delta, triple delta, that is also possible, but all these features I mean we have to see what are the unique advantages of going into such topologies. What is exactly the advantage that we get? One advantage is always there for MMC is that we use modular low voltage devices, but connect many of them connecting together to produce a controllable high voltage source. Okay. That is the inherent feature of MMC. Now, how do we play around with that? How do we play around with these controllable voltage sources is how we make different topologies suitable for different applications. Okay. So, that is what is something interesting about an interesting and also unique feature of the converter. Now, another variant is possible. This is called double delta bridge cell, okay. And sometimes it is also known as a hexverter. Okay. So, this is also possible to have a 3 phase to 3 phase circuit. So, as I told you like you see this circuit is, so basically we are giving a circulating current path in this double star bridge cell, okay, sorry, double delta bridge cell. So, how does it look like? See, earlier there were 3 cells connected, now we are connecting 2, but it is connected in a slightly different fashion. You see, this is one, the upper, see the upper arm and the lower arm. Okay. So, the upper arm and the lower arm and the upper arm and the lower arm, okay, for each phase. But there is a circulating, there is a path for the circulating current, because remember the circulating current must flow inside the converter to maintain the energy balance. So, the path of the circulating current is something like this, going like this. So, this is the circulating current path, goes like this, goes like this, and goes like this, and then again goes back. Okay. Sorry, I have done mistake, not like this, not this one, it does not go back here. So, pen, and then it goes back through here, and through here. Okay. So, this is the path of the circulating current. So, here also what is the advantage here? In this earlier version we had 9, we had 3 plus 3 plus 3, total 9 controllable voltage source or 9 arms that we had to do. Okay. But here in this configuration we have 6 controllable voltage source or 6 arms. Okay. And in with this 6 arms it is possible to have a 3 phase to 3 phase converter. Another way of another way of drawing this circuit, that is why this term hexverter came. Another way of drawing this circuit is something like this. Okay. So, you see there are several okay. So, you can have 1, 2 and 3, this is the one AC system and the other AC system is like this. Okay. So, this is the same circuit, these two are same circuit, but I am again drawing it in a different fashion. So, you can clearly see the ABC and A dash B dash C dash system connected through the converter. That is why this is typically looking like a hexagon. So, the author who had proposed first, it called it as a hexverter. So, and you have a, you see there is a path for the circulating current here. This is the circulating current which will be flowing. So, this is the circulating current which is flowing through the 6 arms. Okay. So, this is also possible with such a converter, 3 phase to 3 phase conversion. Now, what about DC to DC? In fact, yes, MMC is considered to be a very promising solution for DC to DC conversion. Now, why DC to DC? Because if you have something like an HVDC transmission system and you have some renewable energy sources which is close to this HVDC, and suppose you want to inject the renewable energy source directly into the HVDC grid, okay, or you have a load, okay, and the HVDC line is going, you want to tap some little amount of power from that HVDC into the local load. Okay. Often it is found out that sometimes the HVDC lines are going through remote places where the grid is not so, means there are places where the power is flowing through HVDC line, but the local loads do not get, the grid is far off from there. Okay. So, in India it happens many times that the HVDC line is going through a remote area where there is a possibility of a lot of, say, solar energy generation or hydel power generation. If we can directly integrate these energy sources into the HVDC grid, something called as an HVDC tap, then it may be very, very useful. Okay. We can directly connect that energy source into the HVDC grid. So, so such a thing, so then we will need a DC to DC converter. Okay. We need a DC to DC converter for, suppose this side then becomes an HVDC and this is an LVDC or MVDC, medium voltage or low voltage DC. It is possible. Okay. So, again we use these controllable voltage sources or cells in such a way that as if like we are taking one, let us say it is very similar to the voltage divider circuit. Okay. So, we get, so this is one HVDC and this is what we get, a fraction of this one, a fraction of the DC voltage. So, isolated versions are also possible. So, isolated versions means, say suppose you have this HVDC and then you have a large number of cells and there is also, so there is an arm inductor and then there are number of cells like this, and you can have like this, and you can have a high frequency transformer here. You can have a high frequency transformer and then, so what this is doing, this is DC and here you get a high frequency AC. Okay. High frequency means, say because this is at a very high power level. So, high frequency means instead of 50 hertz we may go to 400 or 500 hertz. Okay. So, because this will be producing a high frequency AC here, 500 hertz AC, which we pass it through a transformer, get the isolation, and here then we convert it back. We will have a rectifier, either we can, so we will rectify it here and we get the DC here, right. So, this rectifier can be MMC, it can be other types of converter because the voltage here may be less. Okay. It can be MMC or other types, this rectifier here. So, because this side voltage, this is V1 and this is V2, these are also possible. So, you see here that what I want to stress, yeah, so we will see this. So, what I want to stress here is that a large number of possibilities exist. Okay. A large number of possibilities exist when the MMC blocks or MMC cells are used, and the way to analyze it is to think like these cells working together are controllable voltage source, okay. And these controllable voltage are tweaked or controlled or manipulated in such a way that we get the desired output from the converter, okay. So, you can convert AC to say one AC frequency to another AC frequency, convert from single phase AC to 3 phase AC, convert from AC to DC, DC to AC, even DC to DC also. So, that is why the possibilities with this converter is huge, and so people are very much attracted to this topology.